In the previous lecture, we derived an expression for the work done by the gravitational force in a limited region where the gravitational field is constant in both magnitude and direction, like when an object is close to the Earth. Since the m and g are constants, under these conditions, we could write the work done by gravity this way. Let us go back to the equation for the change of kinetic energy of mass m and write the net force as the sum of the work done by the gravitational force due to the Earth and the work done by all the other forces acting on mass m. Now let us substitute the expression for the work done by the gravitational force. Next, we collect the terms that are the changes of energy together. This, in turn, can be rewritten this way. What is the purpose of this shuffling of the work done by the gravitational force from one side of the equation to the other? It is to show that the special way Wg is written, that is, as a change of a function that depends on the position of the object in respect to the other mass involved in the gravitational attraction, can be thought as a change of another form of energy. This form of energy is called gravitational potential energy, Eg. While Ek is energy related to motion because it is zero if the object is not moving, Eg is related to the spatial arrangement of the masses that exert a gravitational force on each other. The higher the height, the more gravitational potential energy there is, and the change of that energy can be quantified with the expression delta mgh. The sum of the kinetic energy and the gravitational potential energy is called the total mechanical energy. Let me do an analogy with an economical situation. The Ek is like the cash in your wallet, a form of money readily identifiable as being worthy. Eg is like money stored in a bank account. The sum of Ek and Eg is like all the money you possess at a particular instant. This sum can change in the future if withdrawals and deposits are made either to the bank account or to the wallet. This is the role of W not equal to G. However, this analogy with economic quantification breaks down when you deal with the numerical values for the potential energy, which varies with your choice of the location of the zero height. We will need to know the choice of the location of the zero height to quantify the gravitational potential energy. Alternatively, you can choose the location of the level of zero gravitational potential energy instead. However, this choice will have no effect on the change of gravitational potential energy. If there are other conservative forces exerted on the object, the work done by these forces can also be replaced by changes of potential energies, and these potential energies can be part of the sum leading to the total mechanical energy. So let us have a look at the relationship in general between a conservative force and its potential energy. Essentially, if a force is conservative, there exists a scalar potential energy term EP such that the tiny amount of work done over a tiny displacement delta dj must be equal to minus delta EP. Isolating for the tangential component of the force gives this relationship. This is a ratio of tiny changes, and as they become nearly zero, the right-hand side of this equation represents the negative of the slope of the tangent to the curve of the potential energy versus the length traveled. Since a positive delta EP leads to a negative FC parallel, the tangential conservative force points in the direction of decreasing potential energy. A graph of EP versus the length traveled is easier to comprehend with a straight line trajectory, so let us study the example of a projectile moving straight up from the zero height. Here the height would be the length traveled, and the graph would look like this, since EG is a line with a slope equal to mg. So evaluating the negative of the slope of the tangent to the curve of EG versus h is minus mg, which is of course the tangential component of the gravitational force when the object is moving upward. Let us go back to the equation relating the changes of the kinetic energy and the gravitational potential energy to the work done by all the forces but gravity. Using the definition of the total mechanical energy simplifies the equation to this. Let us deal with the special case where W not equal to G is zero, so the case where the non-conservative forces are not doing any work. Using the definition of the change of total mechanical energy leads to this, which of course is the same as saying that the total mechanical energy did not change. We call this situation a case of conservation of total mechanical energy. Reusing the definition of total mechanical energy gives this equation. It does not mean that the speed and the height of the object does not change. It means that the sum of the kinetic energy and the gravitational potential energy stays constant. What the kinetic energy loses, the gravitational potential energy gains, and vice versa. Let us revisit an example that was presented in a previous lecture and approach it with the concept of potential energy instead. We will first set the location of the zero height at the bottom of the hill. It is a choice. It could have been elsewhere. However, with this choice in mind, the height at the top of the hill is also the vertical dimension of the hill and the initial height. The givens are the initial height, the final height, the initial speed, and the fact that the roller coaster is frictionless leads to the work done by friction to be zero. The work done by the forces that are not gravity is the sum of the work done by friction, which is zero, and the work done by the normal, which is also zero, because the normal force is perpendicular to the displacement. This is a case of conservation of total mechanical energy, which means that we can use this equation. We can remove the mass from both sides and isolate for the final speed. Again, we only keep the positive root because we are looking for a speed. It is time to substitute the givens, get the final answer, and express the final statement, which is, of course, the same answer that we had found before. This example is just a modification of the previous example where the roller coaster is no longer frictionless, so that the final speed at the bottom of the hill is no longer the one predicted by the frictionless case. Let us start with the same setup for the zero height as before. The final speed is now a given, and the mass of the cart as well. Our list of givens now includes the initial height, the final height, the initial speed, the final speed, and the mass. This time, we are trying to evaluate the work done by friction, which is the only force other than gravity that is not zero, because, as mentioned before, the normal force is not doing any work since it is perpendicular to the displacement. The work done by forces other than gravity is equal to the change of total mechanical energy. This change of total mechanical energy can be written this way. We could substitute the numerical values of the givens at this stage, but let us first factor out the mass and also use the fact that the final height is zero. Now the substitution of the numerical values gives this, with a final numerical answer being minus 54 kilojoules. 1 kilojoule equals 1,000 joules. The fact that the work done by friction is negative should not be a surprise. since the kinetic friction force is in the opposite direction to the displacement. Here is our final statement. Now that we have covered the concept of energy, some forms of it, and how it can change, we can also quantify how fast the energy of an object can change. This will be the subject of the next installment.